Here are the sample problems for Class 3 of Math 117. First problem is to prove that the collection of all two-element subsets of the positive integers is a countable set. And when I say prove it's a countable set, what I mean is specify a way of enumerating the elements, of establishing a correspondence between this set and the set of counting numbers. Here's a nice diagonalization approach to this. We'll list the first element of the set vertically. We'll list the second one horizontally. And so we'll have two-element sets like 1, 2, 1, 3, 1, 4, 1, 5, 2, 3, 2, 4. You're starting to get the idea, I assume. Here is 3, 4. And now we'll enumerate them diagonally. We'll go up this diagonal like that, and with a sum of 3, we'll get the set 1, 2. Then we'll go up the next diagonal. On that diagonal, the sum is 4, and we get 1, 3. On the next diagonal, the sum is 5, and we get 2, 3, followed by 1, 4. For a sum of 6, we will get 2, 4, 1, 5. And you can see I have established a correspondence between these two-element sets and the counting numbers 1, 2, 3, 4, 5, 6, and so on. There are lots of equivalent ways of getting this same result. By the way, using this trick of enumerating in order of increasing sum, it's easy to show that the collection of all n-element subsets of the positive integers is a countable set. And you will be proving that a countable union of countable sets is countable. That allows you to prove that, remarkably, the collection of all finite subsets of the positive integers is also a countable set. Next, here is a nice way of proving uncountability of a set. So my sample space consists of 1, 2, 3, and 4, and we're looking at a function f whose domain is the sample space and the codomain is the power set of the sample space, denoted 2 to the omega. So we've got a concrete example of this. F of 1 is the set 1, 3, 4. Now here's what I'm going to do. I'm going to construct a set x that cannot possibly be in the image of the function f And here's how I'm going to do it. It's going to consist of all elements n with the property that n is not an element of Fn. So let's consider how that works. F of 1 is 1, 3, 4. In other words, 1 is an element of F of 1, and therefore I don't want 1 in my set X. I look at 2. F of 2 consists of just the single element 4, so 2 is not an element of F of 2. That means that 2 will be contained in X. Similarly, F of 3 is 1, 2. That's a set that doesn't contain 3. So 3 is not in F of 3, and therefore I will include 3 in X. Finally, F of 4 is 1, 2, 3, 4. That includes 4, and therefore I don't want to include 4 in X. In other words, my set X in this particular case is the set containing 2 and 3, and there is no way that F of n there is no way that for any n, F of n can equal X, because there are only two possibilities. Either n is included in X, it's 2 or 3, in which case that element shouldn't have been in X, or we consider an element that's neither 2 nor 3. In this case, it's 1 or 4. In that case, F of that particular n does not include n, and it should have been included in X. Here's an equivalent way of looking at this that you might prefer, because it's the same as the diagonal construction that shows that the real numbers between 0 and 1 are uncountable. I can specify that F of 1 is the set 1, 3, 4 by putting a true in those positions and putting a false to show that 2 is not in F of 1. Similarly, since F of 2 is 4, we have a true in position 4, 3 falses. Since F of 3 is 1, 2, we have that. And since F of 4 is 1, 2, 3, 4, we've got 4 trues. Now, circle the elements on the diagonal. And reverse that TFFT to get FTTF. That's another way of representing the set containing just 2 and 3. So this construction is really the same as the construction that you have learned how to use in showing that the real numbers as represented by infinite decimals are an uncountable set. Next, Let's review the proof of a very important result about limits. Namely, that if you have a bounded increasing sequence of real numbers, it has a limit, and that limit is the least upper bound. So we've got this sequence, a sub n. We're told that it's bounded, and any bounded non-empty set of real numbers has a least upper bound. We'll give that a name. The least upper bound is A. So here's A, and there are no elements of the sequence that are larger than that. Now let's consider some positive real number epsilon and think about A minus epsilon. Since A is the least upper bound, A minus epsilon cannot be an upper bound, because if it were, A wouldn't be the least upper bound. Since A minus epsilon cannot be an upper bound, there must be elements of the sequence that are larger than A minus epsilon. So I will choose n such that A sub n is greater than A minus epsilon. But the sequence is increasing. What does that mean? It means that if we choose an integer little n that's greater than capital N, then A sub little n is greater than A sub capital N. And what have we established? We've established that for any positive number epsilon, no matter how small, A minus epsilon is less than A sub n, is less than A sub little n, is less than A. And so for all little n greater than capital N, A minus A sub n is less than epsilon. And that's the definition of limit. One more to go. I want to figure out the sigma field for just the opening die roll in the game of craps. We'll be hearing a lot more about the game of craps in this course. This is my opportunity to explain to you how the game works. So the shooter rolls 2 dice, and there are 3 events we need to consider. The first one which I will call event A, consists of the total die roll being 7 or 11. And in that case, the shooter wins. You can place a bet on this event if you like. The second possibility is that the total on the 2 dice is 2, 3, or 12. In that case, the shooter immediately loses and is said to have crapped out, hence the name craps for the game. The third possibility is that we get some other total, which could be 4, 5, 6, 8, 9, or 10. And in that case, the game continues. Now, the sigma field consists of all events on which it would be reasonable to bet. And there are 5 other events. If you allow the possibility of betting on these 3 events, you also have to allow the possibility of betting on the complement of A. That's the union of events B and C. That's the event that the shooter does not win. Shooter may have lost, the game may continue, but at least the shooter didn't win. There's also the complement of B. Sigma fields are closed under complements. They're also closed on your union, so you can write this in either of 2 equivalent ways. And this is the event that the shooter does not lose. The third possibility is the complement of event C. That is, the event A or the event B happens, and the game does not continue. It's been decided on the first roll. And then there are 2 other events, the empty set and the entire sample space. These are always in a sigma field. So if you want events A and B to be in the sigma field, you have to have these other events. We're going to explore this in much more detail in the next class.